Now let's see another reaction of the alkali metals, the reaction with water. We'll start with lithium.
Okay, and I'm going to pull up Bohr models for each of these. Lithium has 3 electrons total, only 1 in their outer shell. Remember, these are all in group 1, so they only have 1 electron in their outer valence shell. Okay, so we're going to just, I'll pull the Bohr models up as the video plays, and hopefully you can recognize the pattern.
The metal floats on the water and reacts with it, giving off hydrogen gas. Now for sodium. The same sort of thing happens, although the reaction is a bit more vigorous.
Here's sodium. It's got more electrons. It's the next one down in the group, but still just has 1 in the outer shell.
All the alkali metals react with water in the same way. Let's see an equation for the reaction. Hydrogen gas is produced, and the metal dissolves to give an aqueous cation with a single positive charge. Now for potassium. This time you'll see a flame. The heat given out by the reaction is produced so quickly that the hydrogen gas catches fire. It burns with a lilac flame. The next element is rubidium. This time we put a safety screen between us and the reaction. You can see that things gradually become more terrifying as we go down the group. Let's try cesium, our 5th alkali metal.
All right, so essentially what is happening here is the further down we go in this group, the more reactive they get, right? So that should have been the answer on one of your labs. They get more reactive with water. And the reason that's happening is because of this trend where we have 1 valence electron in the outer shell in all of them, right? But essentially what is happening, we're going to learn more about this next chapter. The valence electron in the outer shell is the one that always makes the chemical bonds. Okay, throwing these little chunks of these alkali metals into the water, and they're reacting with the water. Okay, but only this outer shell electron can participate in the reaction. Like, let's look at cesium, for example. It has all these electrons, and this one that's out here really far away from the positively charged nucleus, because remember, we have our positive protons and neutrons in there, and we have our negative electrons surrounding it. Well, this far electron out here is going to be snatched up by another atom or element really easily. Okay, so that's why these ones in group 1 make bonds really easily, is because they are so willing to lose this electron in their outer shell, this 1 electron that they have, right? So they bond really easy, but it also makes them really, really, really reactive. Here, this is just a demonstration of the valence electrons and why, things get a little bit more tense typically in a group. But yeah, I just wanted to connect it back to the lab and show you a real application of what that is. So you can always think, when you're trying to remember which way the groups or periods go, or which trends we're following, just remember this first column, alkali metals, and remember this video of lithium kind of fizz. This one had a little bit bigger and reacted faster. This one caught on fire. This one started making explosions, and this one broke the glass. Okay, so you can know that, okay, group 1, these are all in the same family, group, column, however you want to think about it, because they have similar properties, because they all have 1 valence electron. All right, this is just an example, but as I said in the last slide, that trend increases as you go towards the right. So all these over here have 8 valence electrons, and they're actually a lot more stable. We'll talk about that later. Okay, the second way that the modern periodic table is organized is by rows. Rows go from left to right. They go across, like, so here's row 2, here's period 2. Okay, period 2. So they are organized in this period because they have the same number of electron energy orbitals. Orbitals are, remember, those shells. So everything in this first row has one energy shell, one electron shell. Everything in this row has 2 electron shells, 3 electron shells, and so on and so on. So here's an example of period 2. Here's lithium. Okay, in period 2 we have 2 energy shells. Here's lithium. It's got its 3 electrons because its atomic number is 3. That means it has 3 protons and 3 electrons, right? So we have three electrons. Only 2 can fit in the first shell, so that first shell is filled up for everything past helium, right? Lithium has 1 more, so it's got 1 valence electron in its second shell. Same with beryllium, it's got 2 valence electrons. Boron has 3, so we're going across here. So lithium, beryllium, boron's over here, carbon is here. It's got 1, 2, 3, 4 valence electrons in its second shell. Nitrogen has 1, 2, 3, 4, 5. Oxygen has 6. Fluorine has 7. Neon has 8. Okay, so you notice that they don't actually gain an extra energy orbit. They all just have 2 energy orbital shells, electron shells, however you want to say that. There's lots of different ways to convey that. Okay, and then so the number of shells increases as we're going down in periods. So like I was saying, period, here's this question from the homework. Why does the number of elements vary from period to period? Well, for instance, period 1 only has 2 elements in it. Well, that's because in the first shell, only 2 electrons can fit. In the second shell, 8 can fit. In the third shell, 8 can fit. In period 4, 18 can fit. In period 5, 18 can fit. In period 6, 18 plus however many are down here can fit. I think it's like 32 or something like that. So this changes based on how many electrons actually fit in the orbital shell, and it's a very fixed thing. So the first shell can only ever hold 2 maximum, okay? The second shell can only ever hold 8 maximum, and then once you have an extra one, once you have 11 electrons total, that 11th one goes to the next energy shell. Okay, so the number of elements varies from period to period based on these energy orbitals. Okay, I hope that makes sense. Okay, and then the third way that the modern periodic table is organized is by the atomic number. We just reviewed that, but how about one more time? What is the atomic number signifying? Yep, well, it's right here on the screen. Number of protons, it's also the number of electrons. So Mendeleev, he organized his based on the mass, but the mass was like almost always correct in order, but once you start getting into these bigger elements, you notice that the mass changes. Like let's look at tellurium, for example, and iodine. So we have antimony over here, 121, and we have tellurium, 127, and well, iodine is 126. Well, Mendeleev didn't want to put iodine here because iodine matched the element properties in this group instead of in this group. Okay, so he was like, well, this isn't really following my rule, but I think that the properties are more important in this case. So we don't organize it today based on their mass. I mean, for the most part, it kind of holds true, but there are those examples where it doesn't. All right, so we organize it by the atomic number, and it increases as you go from left to right and then bottom to top, or sorry, top to bottom, kind of like you're reading, okay? And again, this is the number of protons. So like zirconium has 40 protons. Niobium has 41 protons, and so on and so on and so on. So that's the third way that it's organized. So those 3 ways you need to know. As a review, 3 main ways that we're organizing is the groups are organized based on their similar properties, which equates to their same amount of valence electrons. The periods are organized by the number of electron energy orbitals they have, right? Do they have 1 energy orbital, or do they have 6 or 7 or whatever it is? And then the third way is by their increasing atomic number. A lot of you guys kind of guessed on this one or got it wrong on the homework. Does selenium, right here, does selenium have more in common with sulfur or bromine? Okay, so a lot of you guys put bromine because it's right next to it. It has a similar mass, has a similar atomic number, but it actually is sulfur because it's in the same group. And remember, group is our properties. So sulfur and selenium and oxygen and tellurium all have 6 valent electrons in their outer shell. So they all have very similar properties. Okay, so here we go. Selenium has more in common with sulfur because they're in the same group column, which means that they have the same number of valence electrons and similar physical and chemical properties. All right, and then lastly, we have section 5.3, representative groups. Okay, and then we have this question from the homework: why don't the elements within the same group or within the same group have the identical properties? Well, essentially, they're going to have similar properties, but they're not going to have identical properties. And let's just watch this little clip from that video again.
There are 6 alkali metals: lithium, sodium, potassium, rubidium, cesium, and francium. They're all soft metals which can be cut with a knife. In air, the elements quickly become coated with compounds that form on the metal's surface. Here, for example, is lithium. When we slice it, you can see the metallic luster, but the black coating quickly reappears. Sodium is kept under oil to prevent reaction with air. Again, when we cut it, the metal's surface can be seen. But this time, corrosion occurs even more quickly. With the next alkali metal, potassium, the corrosion in air is so quick that it's hard to see the metallic luster at all. As we go down the group, the elements seem to react more quickly.
Okay, so this is saying that they have this similar property of reacting with the air and becoming corroded on the outside. But as you go down, that happens faster because those reactions are happening faster. So they have a similar property, but it's not identical. Okay, so nothing is ever going to be identical. No elements are ever identical. All right. So the answer to this question is, oh, you can't even see it. Essentially, they have the same amount of valence electrons, but they have different number of energy levels, okay? So you have to think about both of those things for this question. It's their group, they have the same number of valence electrons, but they're each in different periods. So lithium has 2 energy orbitals. Sodium has 1, 2, 3. Potassium has 4. Rubidium has 5. Cesium has 6, and so on. And last but not least, why are some metals like cesium usually stored in gas or oil? Well, they kind of mentioned it in the last video. Remember, sodium was stored in oil, so it didn't react with the air. Well, that's essentially how a lot of these super reactive, like alkali and alkaline earth metals, are stored, because they can react with elements in the air or in water, or because there's water vapor in the air too. They actually store them in either oil, like submerged in oil, or they'll store them in containers of gas. Okay, so like cesium, they store cesium, this super reactive one, in containers of argon gas. And they do that because the stuff on this side is super reactive and the stuff on this side is way less reactive. Like these noble gases are super happy with the amount of electrons that they have, so they're very hard to react with. They're very unreactive. Okay, so the answer to this question is that, we store these very reactive metals in stuff that is very unreactive, and that can be in oil or it can be in a gas form. This prevents them from reacting with elements in the air or near their surroundings, okay? So that's another trend where we have high reactivity on the left side of the periodic table, and as we increase and go to the right side, we have lower reactivity. Okay, and we'll learn a lot more about that in the next chapter once we start talking about chemical bonds and chemical reactions. All right, hope this review video helped. Now go and take your quiz, and then you're done with work for the week and POW with quarter 2. Good job, everybody.